Hey everybody. Today I want to go way back to the basics, basic controls. If you've been watching my YouTube channel and are super advanced in the controls, this video is not for you. Let's say almost 10 years now is when I started the controls industry, and I, honest to God, didn't even know what a VAV unit was. I even tried to Google it and everything, and I really had no understanding of what it was. And I got hired, and I soon found out what it was. So I want to share some of that knowledge to people that might be looking to get in this industry, or even some mechanical companies that want to dabble in controls. The way you can kind of know what the stuff does and how to control it. So today, we're starting Basic Controls 101. And we're going to start with VAV units. So VAV units and how they work. So what are VAV units? VAV stands for variable air volume. And sometimes it's called a fan power box, a terminal unit, damper, controls damper. I've heard a lot of different terms for it, and mostly they're interchangeable. So all the VAVs will have a damper that can close or open to control the room's temperature based on air going through the room, right? Now some of the older VAVs are plunger style. They kind of go in and out. Most of the newer stuff are damper style. They turn. It's a damper that opens and closes. More air goes through or less air goes through. So here's the following examples of what VAVs look like. This is the very simplest form of a VAV. It's literally a round damper with a shaft coming out the side. That's where you're going to mount the controller or actuator. And that controller or actuator is going to turn that damper inside that round duct. Obviously, this is going to be attached to ductwork. You're going to have an air handler on one side pushing air towards the VAV. And the outside, you're going to have a diffuser in the ceiling. You look up in the ceilings every day, those are diffusers. So as this damper opens, obviously more air goes through. As it closes, less air goes through. Here's basically the same thing. It's just this has a velocity tube in it. So it could pick up velocity pressure. Velocity tube is kind of like a pitot tube, sort of. We got holes on one side. This is the side facing the air handler. And as the air comes down, it's going to go through those holes at a higher pressure than the holes on the backside. There's a high tube and a low tube. The high is the one facing the air handler. The low is the one facing away from it. So as the air pushes on it, there's going to be more high pressure than low pressure. The next one is a VAV with a hot water coil attached to it. So you can have reheat on the VAVs. Most typical VAVs are supplied with 55-degree air year-round, Fahrenheit. I'm in the US, so I go by Fahrenheit. That's about 13 degrees Celsius for anyone not in the US. So most of the time, most cases, the air handler is always going to supply 55-degree air to the VAV. Now the VAV can kind of shut itself down a little bit and provide less air to the room, but if that's still not enough and it's still overcooling the room, then you need a reheat. This would be a hot water reheat. You would have a valve with an actuator on it, and the controller would open the valve as needed to reheat the air to warm the space. On top of water cooling, you could actually have electric cooling. See, since this has a disconnect and high voltage signs in here, this fan power box is going to have electric heat strips. This side goes to the air handler. This side goes to the space, the diffusers. The electric strips are going to be on the far side from the controller. The controller is actually going to sit in this box. The damper probably comes through right about there. and there's a controller sitting in there, and that's what's going to open and close. Now, electric heat, you obviously have to have some airflow through there. You have to have airflow through there, uh, or else the heat strips could catch on fire. This is a dual duct box. All a dual duct box is basically two VAVs put together. These sides go to the air handler. Typically, there'd be a cold air on this side and warm air on this side, and they mix together here depending on how much you open each damper, and then this blows out to the space. This is seen on a lot of older hospitals and hospitals in general that just run boilers all year round. It's kind of an inefficient system just because you do have to run a boiler all year round to get the hot air coming through this side and have the cold air, the chillers running all year round to have the cold air coming through this side. When you add a fan to it, then it's called a fan power box. This side would be hooked up to the air handler. This is for the fan, and it's all going to blow out this way. When you have a fan, there's two different types of fan power box. There's a parallel box and a series box. So a parallel is going to pull air from outside the VAV and push it out when based on temperature, right? This is only going to come on in heat mode. So we're going to close off the damper, turn on the fan power box, and now instead of pulling 55-degree air from the air handler and heating it up with the reheat, we're going to pull attic air, might be 60, 70 degrees, and warm it up. So we'll get a lot warmer air coming out of here after it goes through the heat strips, if there are heat strips. Most of the time, a fan power box doesn't have heat strips. A series is different. Now, a series will always pull air from the ductwork, from the air handler. So it's like a booster fan. So a series is going to run in cold or hot conditions. It's always going to be pulling air from the air handler. And there's two types of VAV control. There's pressure dependent versus pressure independent. Let's talk about pressure dependent. So a pressure dependent is a very simple design and it's very cost effective, very low cost. So basically, with this kind of system, there's no CFM calculations are needed. So we could go back to that very first VAV box, the one that didn't have any flow tubes in it. That's all you need for a pressure dependent system. So what it does is in cooling mode, when the space is warm, it opens up the VAV to put more cold air into the space. And then when it's cold, the room's cold, it closes off the VAV to put less air into space. Now, we don't know how much air. That's the drawback of this one. So if your air handler's running super high speeds, you could be overcooling the space, putting a lot more air into the space than what it needs when it opens up. And it's all based on temperature. Pressure independent is different. It's accurate and stable flow control. It eliminates the need for rebalancing. CFM calculations are needed, so we are going to calculate how much air is going through there. And it's the same principle, but it's based on CFM calculations, airflow calculations, right? You're going to have a minimum airflow set in the controller and a maximum airflow set in the controller. And you're going to modulate between those two set points, those two flow set points, based on the room temperature. As the room gets colder or warmer, it's going to modulate more to the maximum CFM. As it gets colder, it's going to modulate down to the minimum CFM. But you need some air, even if the room is cold, you need air circulating in there to do air changeouts, or else the air gets stale. Let's talk about how to wire up the fan and heating controls. Some of you see this and you're already overwhelmed. It's some of the box manufacturers can make it a little overwhelming. Most of the box manufacturers use the same color wire for everything in the box. You'll see a lot of red and you'll see a lot of black. So you have to read the schematics and know how to wire it up. Here's a pretty simple schematic from a train box. All we care about in the controls world is just this area right here. So the top line is our neutral coming off our 24 volt transformer. So it's 24 volts neutral. The next one is 24 volts hot. And that's what we're getting from the transformer right here. And then what we have here is 24 volts going out to the relays, the contactors for the stage 1, stage 2, and stage 3 heat. And what we'll do from here, we'll fire a neutral or a common out to close this contactor. Now the hot has to go through an air proving switch, which is this silver guy right here, which has tubes going to it. So it has to prove airflow for electric heat to come on. So if you have 24 volts going to it and it's not turning on, this is the first place you have to look, is the air proving switch made. So if you have 24 volts going into it but not coming out of it, then either you have a faulty air proving switch or you're not getting enough air volume through your VAV to close the switch. That could be a problem. That's a problem a lot of the time. So you'll have to go and you'll have to open up more air to the room during heating mode. That way you could close your air proving switch and turn on your heat. The next one is stage 2 heating, and the next one is stage 3 heating. Now, I like it when boxes do this because different manufacturers of different controls either send out a 24 volt hot or 24 volt common signal. Johnson controls on the VAV units, on the binaries, actually need to send out a common. So we would put our hot right here and we would close the commons. Some other controls, or even older Johnson stuff, used to switch the hot. In that case, we would need to put the 24 volt common right here on the 24 volt AC, and we would like fire the hot. So depending on the different control manufacturer is how you would wire that up. So that's a VAV system in a nutshell. We get 55-degree air from the air handler and we close it down or open it up to warm and cool the space. And if usually on perimeters of the building, there'll be electric heat or some form of heat. So if closing off the air doesn't warm up the room, then we'll introduce some kind of heat into the room, either via electric heat strips or hot water. Thanks for watching.